In the last video, we talked about how to solve first-order differential equation through the method of separation of variables. But in this one, we're gonna go over the same thing, but we're gonna add solving also the particular solution of the problem. So these problems are a bit more tedious than the last ones, just to help hone in our math skills. And also, we are going to introduce the topic of particular solution. Now, what is a particular solution? Well, a particular solution is a solution to a differential equation that does not contain any arbitrary constants, right? And so I guess a better way to show you what that means is to actually do the problem. So let's go ahead and do that. So we have the derivative of y. So we got to solve the derivative of y with respect to x is equal to y over x times x plus 1 and find the particular solution when y of 1 is equal to 3. Let's do that. So we have the derivative of y with respect to x is equal to y over x times x plus 1. So first thing we want to do is we want to get our variables all on one side. So I'll do that. So we're going to go ahead and we're going to multiply by 1 over y on both sides. So the y will cancel out with this y right here, and then we have 1 over y dy over dx on this side is equal to 1 over x times x plus 1. From there, we're going to multiply both sides by dx. Dx here. Dx here. Dx simplifies with dx, and now we're left with 1 over y. 1 over, ooh, my bad, messed up my pen. I have 1 over y dy is equal to dx over x times x plus 1. From here, we're going to go ahead and we're going to integrate both sides. Integrate the left-hand side. And get the right-hand side. So the left-hand side is pretty trivial, right? This is just 1 over y. That's ln of y, right? It's ln of y plus some constant c1 is equal to, well, to solve this, we're going to go ahead and we're going to have to do partial fraction decomposition. So we're going to separate this into two separate integrals. So when we do that, we have 1 over x times x plus 1. And now we want to separate this into two different fractions, right? So we have a over x plus b over x plus 1. We want to figure out how to separate this. Well, first thing we can do is multiply by the denominator of this left-hand side. So we get y is equal to a times x plus 1 plus b times x. From there, if we split off this a and we distribute it, so we get ax plus a, we'll notice that we can group our x's together, right? Our constants with our x's. So we have a plus b times x plus a is equal to 1. Well, we only have a constant on the left-hand side, so if we only have a constant, then our only constant on the right-hand side must be equal to this 1. So a must be equal to 1, right? There's only a constant here. There's no x's. So that means if there's no x's, then a plus b must be equal to 0. Must be equal to 0. So then we know a is equal to negative b. Oh, I guess a better way to say it is b is equal to negative a, which is equal to negative 1. So we know b is equal to negative 1. We know a is equal to 1. And now we can split this integral into two separate integrals. So we have the integral of 1 over x dx minus the integral of 1 over x plus 1. Right? I just separated out our negative 1 right here. That's our b. And we have our a as well in this left term right here, 1 over x. Now, if we integrate these are pretty simple integrations. These are just all the natural log, right? When we integrate this, we get the natural log. So we get ln of y plus c1 is equal to ln of x, right? It's just like ln of y, except we change their variable. Ln of x plus c2. Then we have minus ln of x plus 1 plus c3. Right, now we want to go ahead and combine all of these constants into the one big constant, right? Because all we care about is one constant. We don't care about what all these smaller constants are. We only care about one major constant. We have L of y is equal to ln of x minus ln of x plus 1 plus c. Now, if you'll go back and remember your properties of natural logarithms, you'll remember that the natural log of a minus the natural log of b is equivalent to the natural log of a divided by b. Knowing that, we can combine these two natural logs right here. Combine them. So let's go ahead and take this right here. We can combine them to be natural log of y is equal to the natural log of x divided by x plus 1 times or plus c. So here we can raise both sides to the e. So we get e ln of y is equal to e ln of x plus 1. Remember your property of exponents. If we have any addition in the exponent, we can change that to be two bases being multiplied by each other. Right, so now we have e raised to the c, so this plus right here, we can just change that to be an e base being multiplied by the other e base. From here, we can simplify a bit. So remember, e's exponentials and natural logs simplify. So we get y is equal to x times, well, e to the c is just c, so we can just go ahead and write that out as c again. X plus 1, right? And now here comes the part where we have to do particular solution. So if you'll remember, we have to find the constant when y is equal to 3. So this is the y is equal to 3 part. And when x is equal to 1. So when x is equal to 1, that's what the x value is. So if we sub them in, we get 3 is equal to 1 times c over 1 plus 1. Well, that's just equal to c over 2. So we get 3 is equal to c over 2. So multiply both sides by 2, we get 6 is equal to c. If we substitute in our value for c, we get y is equal to 6x over x plus 1. And that is how we find the particular solution to a differential equation. Just for the sake of hammering in what we already know, we can go ahead and we can do one more example. So we have solved a differential equation and find the particular solution when y of 0 is equal to 2. So let's go ahead and do that. So we have 1 plus x squared dy over dx plus xy is equal to 0. I want to try to isolate dy over dx. That's usually my goal. So first thing I'm going to do is divide both sides by this 1 plus x squared term. It's 1 plus x squared term. So let's divide everything by 1 plus x squared. Divide this by 1 plus x squared. Anything 0 divided by anything is just 0, so we'll remain right there. So these two simplify right here to 1. And we're left with dy over dx. dy over dx, my bad. dy over dx plus xy over 1 plus x squared is equal to 0. We can go ahead and move this term to the right-hand side, so we get dy over dx is equal to negative xy over 1 plus x squared. From here, I'm going to get our multiply both sides by dx. Multiply both sides by dx. And also, just to make sure this video isn't too long, we're also going to multiply by this reciprocal of y. 1 over y on both sides. Now, what does this do? Well, on the left-hand side, it simplifies our dx. And on the right-hand side, it simplifies our y. So from there, we're left with 1 over y dy is equal to negative x over 1 plus x squared dx. Now we want to integrate both sides. Now, if I integrate this left-hand side, very trivial, this is our natural log. But if I integrate this right-hand side, what I want to go ahead and do is I want to do u substitution, right? So we have negative integral of x over 1 plus x squared dx. If I set this bottom part, to be equal to u, right? So we have u is equal to 1 plus x squared. We find our derivative of u with respect to x. We end up with this 2x. It's 2x. Multiply both sides by dx. We get du is equal to 2x times dx. Well, what this tells me is that if I want to substitute du, I need a 2x dx. Well, what do I have? Well, I have just an x. So how do we get a 2x in there? Well, what we can do is you can multiply the outside by 1/2 and the inside by 2. This is essentially changing nothing. We're just multiplying by 1. But it gives us the tools we need to substitute in the variables we want. Right? So this part right here is going to be oh, my bad. So this part right here is going to be our du. This part right here is going to be our u. Go ahead and show that. So we'll end up with negative 1/2 the integral of du over u. Du over u, the integral is just a natural log, which seems to be the running theme of this. So you get negative 1/2. Let me just write it right here, just so I have a bit more space. So negative 1/2 natural log of u plus c. Well, we're not dealing with u's, we're dealing with x's, right? We're dealing with x's. So I'd want to go ahead and get rid of this u. And we know what u is equal to. We made it up. We said u is equal to 1 plus x squared. Go negative 1/2 natural log 1 plus x squared plus c. So we can go back over here. We know that this is the natural log of y. It's equal to negative 1/2 the natural log of 1 plus x squared plus c, right? Now, if I want to raise both sides to the e, I'm going to go ahead and I'm going to take this natural log. Let's move this up here. I'm going to take this natural log and I'm going to use our properties of natural logs to move this term in front to the exponent inside. Ln of y is equal to ln of 1 over 1 plus x squared. This is the square root plus c. Now I can raise both sides to the e. I can raise this to the e and raise this to the e. So if I raise both sides to the e, what I end up with is y is equal to 1 over the square root of 1 plus x squared. And remember, we can rewrite this exponential right here as the multiplication of two exponentials, one with the natural log and one with the c. So we get e to the c, which is essentially e to the c. That's just another constant, so we can rewrite this as 1 is equal to c over the square root of 1 plus x squared. From there, what we can do is remember we're going to solve our initial value problem. We want to find the particular solution. So if we want to find the particular solution, we need to find it when y is equal to 2 and when x is equal to 0. So y is equal to 2 and when x is equal to 0. So we get c over square root of 1 plus, well, 0 squared is just 0. And the square root of 1 is just 1. So we get 2 is equal to c. Now that we know that, we can substitute in our value for c, and we get y is equal to 2 over the square root of 1 plus x squared. And that is how we solve two different problems for when we want to find the particular solution, also referred to sometimes as an initial value problem.